the perfect speaker to tell us about a love story.
Actually, 3 months later, I married in secret with that young lady over there, so it's really on topic. And just to keep on topic, for the next few minutes, I will tell you a little love story between stars and planets, and I will also add some moons into the story. So, I want to start by defining what is attraction. This is a question that puzzled mankind for a long time. And actually, my favorite theory was proposed by Aristotle, a Greek philosopher, which stated that the nature is divided into 4 elements. So, air, fire, water, and earth. And he states that air and fire belong to the heavenly body, to the heavenly realm. That's why air and fire rise. And he stated that water and the earth belong to our realm. That's why they stick to the ground. This is a lovely idea, but of course we nowadays know that this is not true. This is because we had this guy over here, that I think we all know, Isaac Newton, which stated that if we have 2 bodies with mass, the 2 bodies will attract each other. Some people may call it love, Isaac Newton called it gravity. So, transposing this to a planet and a star. So, in here we have a star, very massive, with a lot of and very big, and in here we have a planet. Due to gravity, the planet will rotate around the star. This is what we call an orbit. Usually we tend to think that the orbits are perfectly and circular, but in reality, the orbits are always a little bit deformed. And we measure the deformation of an orbit by a quantity called the eccentricity. The larger the eccentricity, the more deformed an orbit will be. Now, so far we are looking into the orbits from above. So we have here the star and the planet is doing like this. Let's, oh sorry, I forgot to talk about a thing first. Let's trace a line dividing the orbit over, in middle over here and another one over here. This distance over here is what we call the semi-major axis, which is no more than the mean distance between the planet and the star. And now, let's change perspective. So, from now on, let's look into the orbit from the side, where the planet just goes behind the star, and then it goes above the star. Now, I will just put the head into our star, just to show you that the star is not rotating, but what is actually rotating is the planet. So now the planet, instead of moving in this direction, will move a little bit with a small tilt. This is what we call the inclination. And just to quickly summarize all the things that we need to define an orbit, we need the semi-major axis, which is the mean distance between the planet and the star. We need the eccentricity, which gives us the deformation of the star. And then we need the inclination, which gives us the tilt of the star. So, all of these things are pretty easy, but now I want to complicate things a little bit more. Because, I forgot so this is the actual orbit of a planet. So, when Newton defined gravity, he stated that gravity goes with distance. So, if 2 bodies are very close, the gravity is very strong. If the 2 bodies are far away from each other, the gravity is far more weaker. This means that if we have, in the case of the Earth and the moon is pulling the Earth, and a gravitational force over here will be larger than, let's say, over here and over here. This means that our oceans will be pulled towards the Earth, whereas in this part over here, the oceans will be going down. This is what we know, this is what we all know as tides. Now, taking into consideration that the moon is always rotating around the Earth, in here we are rotating with the moon, that's why we are seeing the Earth rotating. As we rotate, we can see that the high tide is aligned in the moon, and as we rotate, we experience a low tide, then a high tide, then a low tide again, then a high tide. That's why we have 2 high tides during a day and 2 low tides. Complicated thing is that the moon pulls the ocean. and the ocean will be elongated in the direction of the moon. But the Earth is also rotating, and actually the Earth rotates faster than the moon. This means that the high tide will be always slightly ahead the actual position of the moon. This is what we know as tidal lag. And nature doesn't like this. Nature likes that everything is perfectly aligned. So the way that nature arranged to compensate this behavior is to migrate the moon. So to compensate this motion, the moon is actually moving apart from the Earth. So it's like the relation is breaking a little bit. And how do we know that? We know that because with the Apollo missions, actually with the Apollo 15, we let at the surface of the moon a small set of mirrors which we use to shoot lasers and measure the migration rate of the moon. And we now know that the moon is migrating 4 centimeters per year. This doesn't seem a lot, but if we think that in 10 years the moon will migrate 40 centimeters, in 100 years it will migrate 4 meters, so these are effects that take a long time to occur. On the other side, we can also have the moon moving closer to the Earth, and that would happen if the Earth rotates slower than the moon. So you can say that some relations are corrected. So, another effect that tides have on the moon is that as the moon migrates outwards, the moon is slowing down its rotation speed. And nowadays we are in this sweet position where the moon is always pointing the same face to us. This is actually happening to the Earth. As you can see over here, the Earth is slowing down a little bit. A few billion years ago, a day in the Earth was way smaller than it is today. And nowadays we have the moon tidally locked with the Earth, and in a few million years we'll have the Earth also tidally locked with the moon, which means that in a few million years only half of us will be able to observe the moon. The other half will have to do tourism to see the moon. This will only happen in 1.5 billion years, so we can all enjoy the moon so far. So, does that mean that all planets in solar system are migrating and they are tidally locked? Yes and no. So, all planets in the solar system, they are all migrating outwards, but they are not tidally locked. And this is because the solar system is special, and because all the planets in the solar system are far away from the star. This is not true for the exoplanets that we observe. Nowadays we observe more than 5,000 exoplanets, and the majority of them, such as this one, the TRAPPIST one, are very, very close to the star. So these 7 planets over here, they are well within the orbit of Mercury. This means that all these 7 planets over here, they are always pointing the same face to their star, meaning that this side over here, it's very hot, and this side over here, it's freezing cold. These are really not good conditions for habitability. So, let's imagine that the Earth was one of these TRAPPIST planets, and it's very close to the star. Since if the Earth was very close to the star, the tidal effect will be so strong that not only the ocean will suffer tides, but actually our actual planet will deform. And there's a region which we call the Roche limit, that if the Earth actually crosses that region, the Earth will be completely shattered. This is because the deformation will be so large that our own gravity will not be enough to pull us together. This fortunately will never happen to us, because this will only happen if we are at 1.5 radius of the Sun. So good news for us. And how do we measure all these things? We do not measure with love. Actually, our love has a mustache and a monocle, and it's actually this guy over here, Edwin Love, which was a scientist from the 20th century, and he defined a set of numbers which he called the love numbers. I always had difficulties to find a good explanation for the love numbers. Actually, ChatGPT was amazing, and it provided me the best explanation that I saw so far. So, love numbers are dimensional parameters, which just dimensional parameters just say that they don't have units. They are not measured in liters, kilograms, or something like that. And they describe how a planetary body deforms, and they define, it will work one of these days, okay. And they define how a planetary body deforms under tidal force, such as the motion, the perturbation of a moon or a planet. They are fundamental in geophysics, astronomy, and in planetary science. So, let's take the example of Europa. Europa is one of the largest moons of Jupiter. And we think that, due to missions that we sent to Europa, that Europa is composed by a surface made of ice, this part over here, and below that icy surface, we believe that there's an actual ocean, liquid ocean over there. Below that liquid ocean, we think that the interior is made of rock, and then in the core, a lot of iron and a lot of dense core. Then, we can also look at Io. Io was already mentioned in this area today. Io is one of the moons of Jupiter, actually the closest moon of Jupiter, and when we sent a probe to Jupiter, we realized that Io has these plumes over here. These are this is volcanism. Io is so close to the moon, to Jupiter, that is constantly deforming, and all this deformation is leading to a lot of friction within the satellite. All this friction is melting its interior, and it's causing a lot of volcans in its surface. So, just to summarize, we have Io, Europa, and then we have Ganymede and Callisto, the 4 largest moons of Jupiter, and we more or less know their interior composition. And if we measure their love numbers, we can do a funny thing, because imagine that we have 4 exoplanets that we don't know anything about them, and we don't have a way to go there, and we'll never get a way to measure their love numbers, to measure their interiors. But if by some reason we are able to measure their love numbers by comparison, we can more or less infer their interior compositions, even though we will never be able to go there and sample them. This is actually what I do for a living. This is what I wanted to came here to talk about, and I'm happy to take questions now. Is everyone embarrassed by talking about love? Is this? Yeah.
Sorry, I didn't get if you explained how those numbers are obtained.
No, I didn't explain because I didn't have time, but I was expecting that question.
Okay.
I came prepared, right? Yeah. Let me just switch for another slide. Yeah, one of these days again. Okay, yeah, a lot of slides I did. Can you pass directly to the slide where I have to? Sorry. Yeah. So, there's another effect happening. As the tides lead to migration, as I explained, and as the migration occurs, the position between, let's say that they have two planets orbiting around the star. Due to tides, they are migrating, and their position is constantly changing. And usually, if everything is going fine, what happens is that we have a star and we have 2 planets. And they will have close encounters, which are marked by these gray dots over here. If you look carefully, these close encounters will happen in more or less random positions. This means that when they are very close, they will perturb each other, they will attract a lot. But over long periods of time, since these perturbations are happening in random locations, it's like nothing happened. This is what we call a secular perturbation. On the other side, we can, if we have tides, and as the position of the planets change, we can have a mid-motion resonance configuration, where instead of having the close encounters in random positions, if you look carefully, you can see. Can you play it again? Sorry, I didn't put in a loop. Sorry for that. This one. Yeah, I think. Yeah, and this one, please. Yeah. So the close encounters will will always happen at the exact same location. They will happen always over here and always over here. So they will no longer cancel over time. They will enhance the perturbation of the system. They will enhance the eccentricity and they will enhance the inclination. And by measuring the enhance on the eccentricity and the inclination, we can pinpoint the velocity of the tidal migration. And by pinpointing that velocity, we measure the love numbers. This is not easy, but yeah, it's...
Thank you.
Yeah, yeah. Does anyone else have any other question? Yeah?
Can multiple bodies have different compositions but have the same love numbers?
Yeah, that's an actual problem. We can have different compositions with the same love number, so we do a very scientific thing. When you measure a love number, we just pray to be right. Yeah, just pray a little bit, and yeah. Usually what we do is say, okay, we have a love number of, let's say, 0.5. We can have this, and this composition, and yeah. Is anyone that? Yeah.
You mentioned the parameters for the orbit or the eccentricity.
Yeah.
The inclination.
Yeah.
What is the reference plane for the inclination? Is that the rotational axis of the star?
Yeah.
And why is it of influence on the tidal forces?
On the, sorry, can you
Tidal
repeat?
forces.
Okay, so the question is, what is the reference plane for the inclination and the eccentricity? So this differs from person to person. Me personally, I like to use the equator of the star, the spin axis of the star.
Rotational.
Yeah. Personally, I like to use that because for me it's easy. But independent of the reference plane that we use, the science is always the same. It will only become more difficult or less difficult. But for instance, if you talk to an observer, the inclination is a completely different thing. And how does the inclination affect the tidal, the tidal effects? It's quite easy. So the thing is, imagine that you have the planet orbiting over here. It will just do this part over here, and it will always deform the planet in this, this point over here and in this point over here. But if we have inclination, the points will switch. It will change over here, and it will just process over the entire planet. It will do an extra type of tidal interaction. However, the inclination is far less effective, it's far less important than the eccentricity. If we have a large inclination, it will not be as important as a large eccentricity, for the tides, at least. Yeah? Yeah?
Sorry. Is it possible that you will discover another type of interior for the same love number in the future?
It can be, especially because this is a very unexplored field. The story is, this is more or less, this is being done for the solar system for quite a while. And I realized that there was not a lot of people working on this. And during my PhD, I worked with the solar system, and now in my postdoc, I'm working on exoplanets, and I'm realizing that, yeah, it can be a thing. I'm finding a lot of different configurations for the same love number. Yeah, so instead of solving the problem, I'm just making it worse. Yeah.
What's the love number for the Sun-Earth system, and how far away are we from being pulled apart?
Okay, so the love number for the Earth is 0.3. The love number for the Sun is 0.003, and we will never come together because the Sun is rotating faster than the Earth, which means, so if you remember when I said the Earth-Moon system, the Earth is rotating faster than the Moon, so it's the exact same thing with the Earth and the Sun. And so the Sun is moving, the Earth is moving further from the Sun. We will never get engulfed by the Sun. Not unless in 4.5 billion years, the Earth, the Sun, will turn into a red giant, and it's quite unclear if when the sun becomes a red giant, it will engulf the Earth or not. It's quite unclear yet, but
It will burn anyway.
it will burn. Yeah, that's obvious. Yeah, that will happen. Yeah. Yeah.
Sorry, one more question. Is there an explanation of why the exoplanets that we observe have the orbit so close to the star?
There's so we think that there's a thing called observational bias. So it has to do with the way that we measure, that we observe exoplanets. There are very few exoplanets that we measure by directly observe them. So what we do is, as the planet rotates around the star, it creates a small wiggle in the position of the star. So, and the closer the planet is from the star, the more the star will wiggle. So, our current telescopes, we can observe more of these very close-in exoplanets than the ones that are very far apart. Okay, yeah.
You mentioned that the Earth also becomes tidally locked with the Moon in like 1.5 billion years.
Yeah.
And now the Moon is, as we say, already tidally locked.
Yeah.
But I guess technically it's not complete yet because it wobbles slightly, right? So you see like 60% of the Moon is
that's true,
50. Do you know when it completely locks?
Damn, I was thinking about putting that slide over here. I should have put it. No. So the thing is, it's entirely true. If the Moon was full tidally locked, we'll only observe half of the Moon, but in reality we observe 59% of the Moon. That's because the Moon is slightly tilted, which means that the Moon, instead of rotating, it's rotating like this, rotates like this, and it's actually doing this precession motion. This is actually a full tidally locked motion. This is what we call a Cassini state. Please don't make me talk about Cassini states. Damn. Please, no. Cassini states are... It's a Cassini state. Let's give it like this way. Yeah, it's right. Yeah. I don't think there's any more questions, so thanks for having me.